Oh
I
yeah,
know you will.
yeah.
Hey, everybody, welcome once again to Astronomy Daily Live. It's 2 hours UTC, ding, and it is time once again to gather together, grab our preferred consumables of choice. I've got the big mug here again, so cheers. Mmm, fresh batch, great stuff. All right, excellent. So hope everybody's doing well. Things are good here. It's so I got up this morning, 3 a.m. local time, and looked outside, the bedroom window, and saw clouds. So I'm like, okay, well, this doesn't bode well. This doesn't bode well. So I got onto the computer and looked at the satellite loop map, and we actually very soon after 3 or 4 o'clock or so, it actually rained here. It actually rained. Um, so it's like if it's raining, not gonna see very many things. Uh, so yeah, that was a bummer. That was a good series of events that I would have liked to have recorded, but that's how it goes. There are going to be other events like that, and I think what I want to do is I want to see if I can use this for occultations as well. So I think I'll be able to, right? I mean, it's not going to be super incredibly accurate, um, but I'll be able to get to within. I don't know. I should be able to get to within half a second or a quarter of a second um, accuracy in terms of timing and stuff. So yeah, it sort of depends on the exposure time that I choose, and then how long it takes to actually download that image from the camera onto the computer. And like I was saying yesterday, my little test the other night showed that an 80 by 80 pixel image takes, I don't know, probably about maybe about yeah, not even a second, maybe like half a second or so to download. So that's not too bad. And 80 pixels on a side um, at 1 by 1 binning is an 80 arc second square of the sky. Um, so that would work as long as the tracking um, is okay. But all right, anyway, I'm just sort of rambling on, just like I like to do at the beginning, just to kill some time, let everybody come in who is going to come in. So Carolina Sky Astronomy, hey Jim, nice to see you again in the chat. So you might have some clear skies Sunday night and Monday morning. So cool. Yeah, you'll be able to get some planet stuff. Jupiter, Saturn. I think Venus is over there still too. So yeah, that's really great. Hope it's clear. Hope it's clear. Um, First view of Saturn. Awesome. Yeah. And howdy, Chuck. Nice to see you there in the chat as well. And appearing both in the chat and on the panel. Bobby, hey, what's going on over there?
Nothing much. I think I may have the solution of why my software-defined receiving app has been lagging in 1804. If I So what I'm going to do after the show is maybe if I go back to the post audio I usually use my Bluetooth speakers for the receiving. If I set the latency to about 100 milliseconds, I might be able to do something about it.
Well, very cool. Very cool. It looks like you're on top of things there.
Yeah, I was on top of the thing. See about why I'm getting this constant stuttering and stuff.
Yeah,
And
yeah.
it's been like that since there's a new version of Ubuntu. There's lots of problems. There's lots of concerns. But yeah, maybe if you can fix the latency, you should have no problem.
Cool. Very, very cool. Excellent. Excellent. So yeah, everything's good here. So today I took my data, my Messier 46 data that I collected the other night using the blue filter, and I took 200 total images, 4-second exposures. I would say about 20 or 30 of them for whatever reason, mainly when I was correcting the tracking a little bit. My software said, nope, I'm not able to find any kind of discernible pattern, so I'm going to skip this image. So it probably skipped 20 or 30 images. So I was able to stack about 170 total images. So 170. Okay, I'm just reaching out, grabbing this 170 times 4. So stacked, that's like a 680-second exposure. What is that? 11 minutes and 20 seconds, is that right? Yeah. So 11 minutes and 20-second exposure for the blue and the green and the red. They all averaged about 170 images total. And so I did exactly the same thing that I did with the oh, you know what? Yeah, I'm going to have to look into that a little bit. Anyway, the plan is to compare my measurements using the new blue filter with the green filter. So blue and green. I've already got green and red, but now I wanted to look at the blue and the green. The blue and the green correspond to Johnson B and V filters. And if I can find a proper transformation between my blue and green to the Johnson B and V, then I have some scientifically valid data that well, at the moment, just is sort of allowing me to have a nice warm fuzzy feeling. So giving me some really, really good confidence that this system here behind me is performing on a scientific level, right? It's going to be able to produce scientifically valid data that is as good as anywhere else. So yeah, with certain limitations, right? I mean, it is a small aperture, right? It's 0.2 meters, right? It's 8 inches. So really, really small. But I I can easily pick out 15th magnitude stars, no problem at all. And the photometric accuracy there is around 1.5%. So that's pretty good, right? That's you know, within the realm of quality. So anyway, so just for fun, and because I've actually never done it before, so this is another thing I can sort of, you know, put a check mark uh, uh, next to on my list of astronomical things to be done. I can check this one off now. I have collected my own data, red, green, and blue, and I've combined them into a single color image. And I will show you that. I posted it over on my Discord server, but I will show you what I came up with here. All right, there I am. So I'm going to share this really quick, and then we will go over here, and so there it is. So yeah, this is the first time that I've ever done this before, and you know, the red, the green, and the blue aren't exactly lined up, but you know, the colors of these stars are definitely, you know, yellow or red, right? And a lot of them are white, some of them are blue. This side, I noticed afterwards, doesn't really have all the color information, right? So I think I'm missing, probably missing the red component over here. So, but yeah, you know, I've really stretched these images, so you know the stars look pretty big and blobby, but I like that, you know, they're nice and round, and you know, the resolution here isn't too bad, and you know, the planetary nebula here, and you see, I think it's 2438. I've compared this image to you know, other images taken, and yeah, all this is I mean, exactly matches the other images that I've seen of this. You know, all these red parts and the green parts and the blue parts, and as you can see, the background here isn't black, right? It's sort of this dark blue, and I think that's because the blue data was taken with a moonlit sky. So the background sky is just naturally brighter, right? And so a little bit of that blue is leaking through because of the sky brightness. But as you can see, you know, these things aren't exactly lined up exactly, right? I mean, I have to shift these things and rotate them, and I sort of have to iterate on that a few times. So, you know, I mean, I did a quick, you know, 15-minute attempt here, you know, to stack the red, the green, and the blue. And yeah, I mean, you know, you can almost see some interesting structures in here, right? So that is pretty cool. So yeah, I'm pretty happy with that. As I said, you know, these kinds of pictures for me don't really do much for me, but this is something I've never done before, ever. So yeah, I can sort of put a check mark next to that one, and I really don't have any interest in doing that at all. I'm much more interested in the colors, right? That sort of, starts providing me with some information about what kinds of stars these are. And the redder ones are either lower mass or more evolved than the blue ones and the yellow ones. So cool. Yeah. So that came out really, really well. What do you think of that, Bobby? You like that?
That's pretty darn cool.
Yeah. I went over to Cloudy Nights, because I wanted to compare. I wanted to see, how does this image stand up to, what would be probably a pretty decent amateur shot, and this is very comparable to those over there. So yeah, I'm pretty happy with that. For what it's worth, right? And to me, yeah, I mean, it looks pretty, but that's about it.
That looks pretty darn promising.
Yeah. So, well, we'll see how all this goes. I'm hoping, I do have one wish list, and that is to get a set of actual photometric filters. I would absolutely love to get the Johnson Cousins UBVRI set of 5 filters. That would be the bomb. So maybe someday. I've got I can get them, but they're like $800. So we'll see. We will see. Who knows? For now, if I can do the transformations, and I'm still doing really, really well in terms of photometric accuracy, then I don't really have to have those, right? Because I can transform these. But yeah, for the 12th magnitude or brighter stars, I'm getting photometric accuracies less than 0.5%. So that's like mind blowing. It's really, really great. So yeah, pretty happy with that. And for a first attempt at sort of making a color image, I think that's all right. I would.
So Jim is saying Deep Sky Stacker does a really good alignment job of your on your RGB channels.
Cool. Okay, I will have to look into that, because I've just been manually doing it. Right. I've just been loading them into GIMP, and just shifting them and rotating them, and shifting and rotating, and iterating on that a few times to get each image properly stacked. But yeah, there are other ways, other better ways to do that. But this is just a manual stack, and it's okay. I mean, it gets the message across. So, all right, well, cool. So, speaking of pretty objects, I wanted to actually get back to the cosmic horseshoe, which we sort of left floating around yesterday. It's this gravitational lens, and as you can see, I posted the colorized image that we made last night. So this is the full resolution image here, and this is just the red and the green and the blue just added together. So I haven't made any kind of adjustments in terms of brightness or contrast or anything at all. So yeah, I mean, if you want to grab that and do something with it, cool. I think it'd be neat to see what you can do with that. It's a very, very, very rich field. I mean, we are seeing, trillions and trillions and trillions and trillions and trillions of galaxies, of stars, right? So pretty amazing. Anyway, so wanted to find out a little bit more about this, and was looking towards the end of the show and not seeing anything yesterday, but so I ended the live stream and I'm like, you know what, I'm gonna find this thing, and I did. I found it over on Simbad. So it has one of those very, very cool names, which most people sort of just shake their head, and it's like, what is this, right? And instead of trying to understand how valuable it is, it's just sort of ridiculed and laughed at, right? But this is just an object that was part of a survey, in this case called the Sloan Digital Sky Survey. And this first set of numbers is the right ascension, right? 11 hours, 48 minutes, 33.14 seconds. And then this second set of numbers is just the declination. So plus 19, 30 minutes. Come on. 30 minutes, 3.2 seconds. So this name is conveying a very, very useful piece of information, right? That being where it is in the sky. So, that's kind of an important thing if you're going to observe this. So yeah, I've always appreciated those kinds of names, because it gives some very basic fundamental information that you just have to look at, right? It's not like, M2, right? What does that tell you? It tells you absolutely nothing at all. This at least tells you right in the name where it is, and I think that's nice, right? All right. Anyway, let's see. So very, very faint, right? Like.
Chuck Naglin, best way to name them, for sure.
I think so. I mean, look. It doesn't really matter, right? Your names like this are arbitrary, right? So why not make it useful, right? Instead of just having a list, right? M1, M2, M3, M4, M5, right? Where you don't know where they are.
Still an identifier as well.
What's that, Bobby?
Seems to have few identifiers as well.
Yep.
That makes you think that it may not be studied at very much when we look at HST data.
Anyway, let's look here. This is from an image from the Sloan Digital Sky Survey, which is, I think, when they first saw it, right? And yeah, wow, it is like super faint. Faint, well, not incredibly small, but so this is a ground image, right? So this is taken with the telescope from the ground. What we were looking at yesterday, this, right? This is HST data, right? So this is the difference, right? Between sort of, I mean, I would say that this is some of the best that you can get from the ground. Yeah. Maybe not the top best, but it's really, really good data. And you can see.
Now, just out of my curiosity, the Pan stores did at least 2 already up in play. Will the Aladdin light will be able to be updated to receive the Pan-STARRS DR2, or what?
I would assume that at some point they will. Um, but yeah, I'm not seeing it here yet. But that's okay. Okay. Bobby will be right back. Anyway, so yeah, there it is in that context, and here it is according to HST. So that's not too bad. All right, let's go back to here, and as I was saying, very, very faint, right?
It still is a nice, well-done image from the SDSS.
Oh yes, of course it is. Yeah, and this I think was part of the discovery of this object. I think this is when they first saw it. We'll get into the papers here. I started looking at the papers, and it's like, no, I should wait. Anyway, very, very, very faint, right? Brighter towards the red. So U, G, R, I, and Z are the Sloan filters. B and R are the Johnson's B and the Cousins R filters. So B is around blue. I don't remember exactly where it is. 4,800 angstroms. 52, something like that. I'm not quite sure. R, I don't remember exactly where R is either. It's got to be around like 6,300 angstroms. And then yeah, U, G, and R are also in the visible realm. I and Z are in the infrared. So, but yeah, very, very faint, right? Wow, 20th magnitude, right? That's well, you know, the human eye can see to, you know, in a really, really dark sky, and if you've got really good eyes, you can see to about magnitude 6, maybe 6.5, but I'll give you 6, right? So in G, which is sort of the middle of the visible range, this thing is 21st magnitude, right? So that's 15 magnitude, 15 magnitudes fainter, right? Every single magnitude is a factor of 2.5. So if I take 2.5, and I've again grabbed my handy dandy calculator here, and raise that to the 15th power, that's a factor of almost a million, right? 931,000. So this object is about 1 million times fainter than what we can see. So that's why we need big telescopes to see them. Big telescopes, long exposures, you got it. And these guys just barely did it. I don't remember what the exposure times were for the HST data. Should we let's just...
So there's no papers?
Oh yeah, there are some. Yeah.
Like
I'm just going all over the place. Not too many. Okay. But we will get there. Horseshoe, cosmic horseshoe. I just want to see how long the exposures were that we grabbed the other day. I think they were these. Oh yeah. Okay. So these were were pretty long exposures, right? The green one was about half the time of the blue one and the red one.
Now these are now the wavelengths are in nanometers, huh?
The central wavelengths here are in angstroms. Angstroms. So these numbers here, if you can see them, see how it says 475? That is nanometers, right? And it's just an approximation, right? It's actually 477.1 nanometers, right?
Okay.
But yeah, these are
they're usually in the gigahertz range, right?
Well, that's like 5,000 angstroms is 500 nanometers. So yeah, we'd be able to work out what the frequency is, but off the top of my head, I'd have to look that up. But it's no, it's in the I think it might be in like the terahertz or petahertz. Yeah, it's way up there.
Yeah. I usually think like in Cosmos when Carl Sagan was doing it, I usually thought it would be like in the beyond like in the long wave range and stuff.
All right. Well,
we might got back to differ.
Yeah. But anyway, so yeah, these are long exposures, right? Long exposures. 5,500 seconds. So these are long exposures. These are multiple orbits.
Because right? I think radio starts at 3 hertz for sure.
Yeah, something like that. All right. Well, cool. Yeah, let's look at the. So here's a few other names, right? Not a lot of other names, but a few. I think GSC is.
Niji. So 500 nanometers is cyan.
Yeah, 500 nanometers, I would say, is sort of a bluish green. Yeah. That is correct. That is correct. All right, here's some names. Guide Star Catalog 2, Sloan Digital Sky Survey. Here's another survey of some sort. Yeah. So look at that, 9 total references. So this has been studied a little bit, but the one I'd like to start with is the first one, which is the discovery paper. So we'll go over to good old ADS here, Astrophysics Data System. While it's loading, I will take a sip. Freshly brewed. Okay. So the cosmic horseshoe, a discovery of an Einstein ring around a giant luminous red gas. And let's see, where are these folks from here? They sometimes say. So University of Cambridge, Russia, Poland, Germany, France. Nice. So a nice distribution, right? A nice international collaboration. That's pretty cool. So Einstein ring of a diameter of 10 arc seconds in the Sloan Digital Sky Survey data release 5. See, so they found it in data release 5. I think we're up to data release 9 on that now. So it's been out for a little while. This is 2007. Yeah, here. So 2007. So that was, wow, so that was like 12 years ago. Okay. This is the discovery paper. Spectroscopic data from the 6-meter telescope reveals that the deflecting galaxy has a line of sight velocity dispersion in excess of 400 kilometers per second and a redshift of 0.444, while the source is a star-forming galaxy with a redshift of 2.379. From its color, luminosity, and velocity dispersion, we argue that this is the most massive galaxy lens hitherto discovered. Wow. So they used G, R, and I. We can zoom in a little bit here. So they imaged this with the Sloan G, R, and I filters to get these guys, and I think that's pretty much what we're seeing over on Aladdin. I think we're seeing this data, maybe updated, because this is data release 5, and as I said, I think they're up to data release 9 now. So, but yeah, you can definitely see that there's it's not a complete ring, right? It's not a complete ring. I think they set up here something like 300 degrees, right? So almost all the way around. So there you go. Inset shows a 16 by 16 arc second cutout. The bluish color of the ring with a really, really red lensing galaxy there. Cool. That's nice. Let's see. Let's see what else they got here. So they're working out little geometries and identifying. We scientists like to identify and categorize things as quickly as possible. So yeah, that's what's happened here, right?
So we just never heard of a a gravitational lens until now, huh?
Well, yes, these had been known, but this is apparently the largest gravitational lens known to this date, right?
So there are many more lenses out there in space, huh?
Yes. In fact, if you do a Google search for Einstein, I think they're called rings. So that one's at the front. That's kind of cool. Let's see. So here's some other ones. Right?
Looks like a smiley face.
It sure does, doesn't it? I think it's yeah. I don't think that's anything. I think it's just a smiley face up there. Yeah. So yeah, some interesting things going on here. But even if you look at this distorted galaxy here, you can see that there's a dark cloud going through it, and maybe a nucleus here, right? So maybe we're only seeing like half of this galaxy because of the lensing effect, right? This one here might be the same galaxy, right? Just on both sides. And this is sort of is kind of interior to this outer ring. So I don't know if that means that that galaxy is closer or further away. I guess it'd have to be. Oh, I don't know. I guess it'd have to be further away, right? Because the further away it is, the more. Oh yeah, I don't know. But anyway, so there's another one, right? And I think we know about a lot of these.
There's a lot of galaxies in that shot, says Jim.
Oh yeah, yeah. So here's some other ones. So yeah, you know, they're sort of all over the place. You just have to look for them. So yeah, this one is definitely not unique. It's I think that at least their claim here is that this is the most massive one they've seen. But you know, this is 07, so things might have changed since then. Let's see, what else do we have here?
Now, on traditional telescopes, you won't be able to find that object at all, right?
Absolutely not. No way whatsoever. You need a long exposure and a big scope. I think the Sloan Digital Sky Survey, we can find out, but I think those are those 3.5 meter? I don't remember. Let's find out. Sloan Digital Sky Survey. SDSS. Let's see. Let's go to Wikipedia. They might have some quick info. 2.5 meter. Right. So it's a 2.5 meter scope. So it's, you know, I mean, it's not huge, but it's big. And with a decent exposure time, right? Don't know. Should be able to find out what the exposure times were here. Let's see if we can find that out. RG discovery and follow-up. Let's see, previous search strategies. I'm looking for all right, well, we'll keep moving along here. I'm not quite okay, so these are some spectra, right? These are some spectra. Going over at least most of the visible range here, right? We can usually see between 4,000 angstroms and about, I don't know, 8,500 angstroms out, way out here somewhere. So, but yeah, they're showing lots of stuff, right? Ionized aluminum, ionized iron, ionized carbon, silicon. Sweet. There's hydrogen delta. Yeah, I don't know about that. I don't know what G is. What is G? I don't know what G is. H and K lines. Yeah, sorry, I don't know what G is. Okay, so this is the spectrum of the lensing galaxy, right? and this is the spectrum of the lensed galaxy. Right, so this top one is the we can go to this
So
is a
Carolina
spectrum.
Scott. So Jim is using the 5-inch and the 6-inch. Chuck has the camera, but he soon is gonna buy himself a scope.
Cool. Yeah, yeah. Well, a 5-inch and a 6-inch, you are most definitely, absolutely, 100% guaranteed you will not see this. Yeah, this is a pretty faint dude for sure. All right, let's. So obviously two different spectra, right? Two different things going on here. There's a lot of red, right? See how it's brighter here in the red than it is in the blue. So it's very, very red. See, this is pretty flat, right? Pretty flat. Brighter in the blue, maybe. But a lot more, at least a lot more identified stuff, right? Now some of these, I don't know, right? But a lot of these are like, yeah, okay, I see a significant bump there, right? So I can buy that, I guess. Fermat time delay surface. Okay, so they've actually tried to model this whole thing. Cool. That's pretty neat. Star forming galaxy at a Z of 2.379. So yeah, so that's a redshift, and that indicates that it's pretty far away, pretty far. Masses, blah 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 blah. Of fiducial luminosity. I'm not quite sure what that means, but okay, yeah, they're just they're talking about the characteristics of the lensed galaxy, which they're calling the source, and then here's a discussion of the actual lensing galaxy. So, okay. Again, they're trying to model all this to hopefully gain a little bit of understanding. But all right, well, cool, nice. So yeah, they just they're basically saying, hey, it's here, it's pretty interesting. Here's some basic measurements. Here's a couple of models to explain what we're seeing. It's great. Very thorough. I like it. All right, well, what else do we have here? Let's see. We've got to get back here. Okay, so these folks, and it looks like some of them have the same names, right? So it's the same. It looks like it's the same group, right? Hewitt, Warren. Did I see a Warren in here? Nope, there's no Warren. But there is that one, and there is an N.W. Evans. I don't think there's any S. Dye. So this is the same group, and it looks like they're continuing exploring this interesting gravitational lens and have decided to do some models. The other thing that I don't remember is when these were observed. Okay, so the cosmic horseshoe that we made yesterday into a color image, that data was taken in 2010, right? So they made this discovery back in 07, but didn't look at it with HST. And I don't know if it's the same group or not. We can look at the proposal ID and maybe find out. Uh-oh. Well, no, they've got a bug in their code. So we're not going to be able to
major bug indeed.
Yeah, they got a bug in their code. It happens, that's all right. They you're supposed to test your code before you make it go live, right? You put it on sort of a separate area or a completely different server, and you test it, right, to make sure that it doesn't do this. So, but sometimes it happens. It's like, don't. But yeah, it's some back end thing, looking for databases and whatnot. So yeah, it's just the typical palm face. Yeah. Oh well. Okay. Well, we're not going to be able to find out who observed these. Not today, but I would think that these folks would probably be interested in looking at it. So I wouldn't be surprised if these folks had a hand in that. Had their paws all over it, I'll bet. So it's taking a minute to load here. So I'm not going to linger too long on these things, but it's kind of interesting to see what these folks are thinking. And this is kind of interesting, right? Everything's switched to the UK. It's just all UK now. So, in the previous one with some of the same authors, it was sort of all over the place. So, yeah, there was a consolidation. Einstein ring system recently discovered in the Sloan Digital Sky Survey. So these guys, Warren and Dye, came up with some kind of a model to invert the Einstein ring for sets of parameterized lens models. Here, the method is refined by exploiting Bayesian inference to optimize adaptive pixelization of the source plane and to choose between three differently parameterized models. Wow. So a single isothermal ellipsoid, a power law model, and an NFW profile. I don't know what an NFW profile is. See, that, this is what I like about reading these kinds of papers, right? Is that every single paper, and it doesn't matter what really the subject matter is, not necessarily, right? All of these are springboards to either being like, okay,
all the time, Jim. Talk about your state.
What's that?
Check the chat.
Check the chat. Oh, okay, I see. All right. Anyway, these are springboards to further investigation, right? I mean, from here, right? I haven't even looked at the paper yet. I already have a jumping off point, right? I've got a jumping off point right there. It's like, what is an NFW profile? I don't have a clue. They'll probably maybe explain it a little bit in the introduction, I'm hoping. If they don't, that's a path that I could take, to find out what the heck is that? I've never heard of that before. So that, and these references are a history lesson, right? Whatever the subject matter they're sort of referencing here, right, is your doorway into the history of this method, right, that these guys have developed. So I say these papers are like springboards forward and backward at the same time. So it's great, and it doesn't really matter what paper it is. They're all exactly the same in that sense. All right. Anyway, let's see. So the mass within the Einstein ring is 5 trillion solar masses. Okay. So that's a lot of mass amongst the large, unique amongst the large separation lenses, as almost all the deflections come from a single very massive galaxy with little boost from the environment. Yeah, we were looking at these other ones, and there were always, maybe not always, but oftentimes there was more than one lensing galaxy. So that just adds to complexity, right? Let's see here. We apply a semi-linear method to reconstruct the lens mass profile and source surface brightness image. So there's some parameters already. Yeah, I don't know what this NFW, is that what it was called? Yeah, NFW. Don't really see that referenced anywhere. I guess I'll keep my eyes open. Let's see. So a little, that's how these kinds of papers go, right? When you're talking about models, then you're talking about some pretty sophisticated mathematics. That's how that goes. And then this, this kind of mathematics has to be turned into computer code. So, there's one more step in all of that. Lens models. Here we go. So an NFW profile is it doesn't explain much, but it is the Navarro, Frank, and White profile. Profile was introduced in 1996 as a fit to dark matter halos created in cosmological n-body simulations. So an n-body simulation is just, n is like a variable, right? You can choose any number. And usually when it says n-body, that means that n's a large number. But n can be as small as, I suppose it could be 0, but that's kind of pointless. An n of 1, that's kind of not interesting either, it gets really interesting when n equals 2, right? Two-body simulations. It gets extremely complicated once you add a third, and then a fourth, and a fifth, and a sixth, and a thousandth, and a millionth, right? But those kinds of things can be done, and your computers are good at computing those kinds of things. So anyway, that's what the NFW profile is. So, okay, yeah, just some fancy math here. Nothing to get excited about.
That's about it.
Let's see if there's anything particularly interesting here. It looks like they've run through some pretty cool looking models. Yeah, so I don't know if you can. I'm going to try to zoom in here. Oh, yeah, that's much better. So observed ring and lens in the G band, the I band, and the U band. So G and I are both part of the Sloan filter set. U is part of the Johnson filter set. So U is very, very violet, right? I think it's around 4,800 angstroms, something like that. It's really, really, really blue or violet. So anyway, so observed ring and lens, observed ring, and then here's some kind of model, I guess. Okay. Looks like they get more or less the same thing depending on, what wavelength you're looking at. It looks like they're getting more or less the same thing. Almost looks like a pair of headphones, right? Like a pair of headphones. Pretty cool. Oh, yeah, I'm not quite sure what this is getting into here. It looks like some kind of distortion map. Yeah, I'm not gonna try too hard to get into that. So this is just trying to match models to actual data, and you get a sense of how far maybe you're off. But yeah, I'm not quite sure what these are exactly. Have to look a little bit harder at the text to find that out. Northern ring, southern ring, huh?
Looks like a UFO photos.
Yeah.
Or a series of UFO photos.
Yeah. This is the cosmic horseshoe, and an Einstein ring, a gravitational lens object that just so happens to be in the constellation of Leo. So that's sort of the constellation that we've been focusing on for a little while now, and maybe there's some other jewels in there. So I'm not going to completely exile Leo quite yet. I think I want to take another look at it here over the next day or so and see if there's anything else interesting. Because there might be. You never know.
Cool astronomy stuff that we can't see with their small scopes, says Jim.
Yeah. Well, we've entered a very interesting era when it comes to astronomy, and this armchair access to raw data, right? Not JPEG images. I'm talking about the real deal, right? FITS images with actual numbers, right? So great stuff. The mirror. I don't know if you paid attention to this or not, but I think I posted something somewhere that the mirror, yeah, here it is. That's not the right one. Let's see if I can find the right one here. Well, I don't see it right now, but the mirror for the LSST, the Large Synoptic Survey Telescope, that is going to literally change astronomy. Left the mirror lab at the University of Arizona either yesterday or today, and dang, you know, I should have thought about that a little bit, and because I could have actually seen it go by on the interstate, right? They're driving it to Houston. It's supposed to take 10 days to get to Houston. Yeah, unfortunately, I think they probably already passed me up. But I mean, if they're going to Houston, then you've got a pretty good idea as to what path they're going to take, right? And at least some of that is going to be I-10, right, for sure. But yeah, I'm sort of afraid that they probably passed me already, because I'm just outside of Tucson. So I mean, I'm maybe a couple days out, maybe, and it's already been a couple of days. So yeah, I think I missed out on that one.
So I'm guessing since they have to be like careful and stuff, I think like possibly you gotta get law enforcement escort and stuff, huh?
Mm-hmm. Oh yeah, no, they'll block off the entire interstate, right? So you don't want to be
How
behind.
big is that mirror? Says asking Jim.
That mirror is about 25 meters in diameter. So it's a big mother. Big. It was made in the Mirror Lab, right, at the University of Arizona, where I used to work. So, Jim, I don't know if you maybe I'll just point it out and maybe not say a lot about it now. But if you look behind me here, this image here, this is the first 8.4 meter mirror ever made, and this was made at the Mirror Lab, and you really can't see it incredibly well, but yeah, from this edge to this edge is 8.4 meters across, and it when you stood up against it, right, and looked at the surface, it was like a salad bowl, right? I mean, just this deep bowl, right? So this is when it just first came out of the spinning oven, and what it has right now, its surface is a spherical surface, right? Now that's not quite.
And that mirror is in Virginia now, right?
That mirror is just to the north of me right now at the Mount Graham International Observatory. It's one of two 8.4 meter mirrors that make up what's called the LBT, the Large Binocular Telescope, and that is just to the north of me. I see it every single day. So yeah, that's actually two of these mirrors side by side in sort of one building, right? So yeah, I actually helped in a very, very, very small way. Don't think that I made any major contributions, because I did not, right? But in a small way,
you still got paid for it, huh?
I was a part of making that mirror. I was just a member of the staff, so you know, I mean, I was just doing, whatever needed to be done. And my particular task was actually performed a little bit later. Once they got this big huge mirror off and out of the oven, they started polishing it, right? Because like I said, this surface right now is like the surface of a sphere, right? And with telescopes, you don't want a spherical surface. You want a parabolic or hyperbolic surface, right? So a surface that just is a little bit deeper than what would be a circular surface. So that is done with a polishing device that had to be invented sort of on the fly. No one was really expecting to have to do that, and it turns out they did. So they had to invent, this whole new technology, right? To be able to polish these very, very large mirrors. And so once they got the surface to sort of where they wanted it, they needed to find a quick and easy way to check how smooth the surface actually was, right? And so they had to take lots of images, so they could actually look at the data and you determine how smooth that mirror surface is. And that's where I came in. I wrote. I was using a CCD camera at the time that CCD cameras weren't being used yet, right? They were relatively new to all of us in the late 80s, early 90s. So I got my hands on one of the first ones ever made, and after that, I was actually able to use a lot of prototypes and a lot of new kinds of CCD cameras. So that was very, very fun. But yeah, so I had to write the software to grab the data and do the analysis and all that. So yeah, played a very, very small part in making sure that mirror worked as well as it could. And you can barely probably see that there are people behind the mirror here going all the way around. And as I recall, I think in this shot I'm over here somewhere, but you're not going to be able to see me there. I think I've shown that photo on live streams before, so I'm not going to belabor that much. So yeah. Well, see, look, this is why, right? This is one of the reasons why I do not have aperture fever, right? Because I got to play with the biggest mirrors, the biggest telescopes in the world, right? I've already done that. So I don't need, larger and larger and larger and larger telescopes. I've worked at and helped make some of the largest ones in the world. So it's like that cures the fever, right? No more fever, right? It's like I've got a really, really, really great scope right here, right? That can do some really, really, really great stuff. So yeah, it is cool. It's very, very cool. It's very, very fun. Those were good times, and wouldn't trade those for anything whatsoever, right? Yeah, yeah, those were good times. Those were good times for sure. All right, well, that is the cosmic horseshoe. So I think that's absolutely fantastic. They've actually, we didn't actually get through all of it, um, but they talk about these models, right? Um, and there's a paper. The latest one comes from 2015, monthly notices of the Royal Astronomical Society, some kind of lens survey. So, yeah, these are just, identifying lensing objects and saying, let's put an ID on it. Um, so cool. Yeah, they're doing spectroscopy. Um, that's great. Yeah, absolutely fantastic. 4 strongly lensed galaxies with a redshift greater than 2. So our guy would definitely be in that from 2009. So very cool, very nice. It's a fantastic looking object for sure. Looked really really good just with the basic HST stuff, just adding red and green and blue. Looked really really nice to me. So awesome. All right, everybody. Well, I think I'm going to get out of here for now. I'm noticing that it is 3:16 UTC. So, yeah, I think it's about time to get on out of here for today. So, hope everybody has a great evening, a great day, wherever you are. Check the chat one more time really quick. Very cool. Uh, Yeah, you should be happy with a 5-inch Mac. Yes, yes, that you've got gold there, and I'm sure you know that. So yeah, you've got it. You got it made. You got it made in the shade. Um, all right, everybody. Well, as I said, yeah, I think I'm going to get out of here for now. So make sure to hit the thumbs up. Make sure to share this around, spread the word. This kind of live stream, this style, is definitely not for everyone. I totally understand that, um, but I think it's just a lot of fun, sharing the passion, and not necessarily having any particular theme or goal or anything else. Because I am doing this every single day, I don't feel any pressure whatsoever to have to necessarily get through anything really fast, or really be like, man, I've got to understand this now, right? It's like, no, it's like, let's take a look at this stuff, see what we can absorb, and whatever it is, it's pretty nice stuff, right? And if a lot of this is way out of your reach, that's okay. It's way out of my reach too. So we're fine. And what we do when things are out of reach is that we revert back to being 2 or 3 year olds, where we would open a book and we'd look at the pictures, right? And so that to me is an absolutely brilliant thing to do, right? It isn't demeaning or anything else. It's like, when you don't understand the words, you look at the pictures, right? And maybe you can get a little bit more out of that. And most of these words in these papers are yeah, it's like, I have no idea what they're talking about at all. And sometimes even looking at the pictures, it's like, I don't know, right? But that's okay. That's all right. The point here is to sort of swim in the ocean of astronomy, and take a look around, see how it feels, see what kinds of things are out there. And I guarantee we're not going to understand barely anything at all. So, all right, everybody, take care. I'm going to get out of here for now. Peace, cheers, and all that. And I will see you in a little less than one of these Earth spins. So, hold on to your hats.
Live long and prosper.
Live long and prosper, right? And we will see you later. Okay, bye.